ME627 Mathieu equation, unstable region. So let me remind you, the Mathieu equation is this: x double dot plus delta plus epsilon cosine of t times x equals 0. The parameters are delta and epsilon. As we have seen, there are stability boundaries that look like this. This one is at 1/4. Then there is one at 1 something here. Okay, so that's 1 and so on. And over here, this part is stable, which I'm marking in green. And this part is unstable, which I'm marking in red. You will be interested to see that in this region over here, in fact, the stiffness, if you like it, the average stiffness is negative, but the vertical excitation stabilizes it. Okay, so these are interesting things. But now what we will do is we want to look at what is a typical solution in a place like this, for example. So we will tentatively try delta equals 0.22, epsilon equals 0.2. Let us assume that the solution is in fact unstable, or we will change these parameters later. So now the question is, I can start it with an initial condition x0. I can integrate 0 to 2 pi. Why 2 pi? Because 2 pi is the period. Okay, so then I'll get some x1. Now, because this is a linear system, if I start with an initial condition alpha x0, I will get exactly alpha x1. Because this is unstable, now you must remember the monodromy matrix had lambda 1, lambda 2 with lambda 1, lambda 2 equal to 1. So if one of these is bigger than 1 in magnitude, could be positive or could be negative, then the other one has to be less than 1 in magnitude and of the same sign. Okay, so the one that is less than 1 in magnitude, let us say this one, it contributes to a decaying component, and eventually, if I keep rescaling this to unit magnitude every time, then eventually it settles into the unstable direction, right? So x1 goes to x2 goes to x3 as I keep integrating, and then aligns with unstable eigenvector. Okay, so this is something that we know from theory, but it is good to see it, and we will see it using MATLAB. So let us go to MATLAB here, and what I will do is I will open a new script file, and I will say function x dot equals Mathieu tx. Then I will say delta equals 0.22, epsilon equals 0.2. That is what we had here, right? We'll try those. We will say x dot is equal to x2 and then minus delta plus epsilon times cosine of t times x1. That's our Mathieu equation. Okay, now what we will do here is let us look at the Floquet multipliers. okay, just to see, because that is our theory. So what we will say is E equals I2, we'll say OP equals ODE set. That's fairly tight. I will say for k equals 1 to 2, Tx equals ODE 4, 5, Mathieu, 0, 2 times pi E k, that's the initial condition, OP, and then I will say E k equals x and transpose end. And so once this loop is evaluated, I have my monodromy matrix, which is here, and I look at the absolute value of the eigenvalues of E, and you can see one of them is 1.85. So definitely it is unstable. More than that, I can take the eigenvectors, and so what I can do is Vd equals eig E, and you can see that corresponding to this eigenvalue, I have this eigenvector 0.9336 and 0.3582. The eigenvalues are both negative. The product of the diagonal terms of D is 1. Format long answer shows you that it is 1 to as many digits as we need. Remember, this is about 12, and that is because this is 10 to the minus 12. Okay, so it's as accurate as our ODE solution. All right, so now I have the V1 and the V2. These are the initial conditions. Now let us see what happens here. Let us take Tx equals ODE 4, 5, Mathieu. Let us take 0 to 6 times pi, that is 3 periods. Let us take V first eigenvalue. Now you must understand what will happen here is that I have chosen the stable direction. Okay, so technically the solution should go to 0, but this growth direction remains, and for this reason eventually it will diverge, but over such a short time I hope that it will decay. So when I look at plot T and X, you see it seems to be decaying. I can let it run a little bit longer. See, from 0 to 2 pi is here, and then from 2 pi to 4 pi is about here, and then it has sort of come down further and so on. That is what it is doing. I can let it run longer, but it will not be able to sustain it for very long. Eventually the other instability will come in, but let us see how long this one goes. And you can see that it is decaying. This is the decaying part. Okay, if I run it long enough, oh look, that's really stable. So I am a bit surprised, but seems to be really stable. Let us do the following. It may have actually gone to 0. That's the problem. Let me try, not a problem, but that is a numerical consequence. In the presence of instability, it should grow. You can see that it has begun to grow again. On a log scale, it has begun to grow again. It just needs to go a little bit longer. So if I go here, instead of 56 pi, if I go to 64 pi or something, then we should, you see now it has exponentially started growing again. Eventually, if I run it long enough, then it will be very big. So 120 times pi there it has gone, and if I plot it directly, it seems like that initial solution seems like nothing, and this is the growing part. Okay, so that's the growing part. Now let us come here and start it again. Let us go for, let us say 4 times pi, 2 periods, but just start with the initial condition of the second eigenvector, that is the unstable eigenvector, and you will see that it is directly growing, and it is, well, it's come only 2 periods, so it will that this much is 2 pi and this much is 4 pi. The negative has become positive by about 1.85, then that has become negative again, and so on. If I go for 8 pi, you will see it more clearly. Now you can see that it is growing, but now what I will do is I will integrate for 2 pi at a time and show you the result. Okay, so what I will do is I will say x0 equals x end transpose x0 equals x0 by norm of x0. So I have scaled it to unit norm. Okay, this is my initial condition. Now what I will do is I will integrate to 2 pi, and then I will show you this again, and you see it is just the negative of that. Because why? Because the eigenvalue is negative and there is a magnitude of 1.85 or so, which is what it gains every time. When we look here, 1 point, right? So here minus 1.85. So the negative part is retained over here, and the magnitude was removed over here. So if I integrate it again, I'll get exactly the same answer as this one. This will be what I get. That's what it is in the unstable region. But suppose I don't want to go fully into the unstable region. Suppose I want to find a place where this eigenvalue is exactly 1. How do I do that? I can do that with trial and error, of course. So I've got 1.85 now, but I can come here and make it something else. You know, I can make it 0.14 or something, and then do the same thing again. I can say E equals, and then 4, and then I can say the absolute values of the eigenvalues of E. You see, so now from 1.85 it has come to 1.5, and in this way I can calculate very precisely. There are better ways to do it, but let's just do one more so that you can see what I am doing. Initial condition identity matrix. Here's the monodromy matrix. Here are the eigenvalues. And so now it has gone to about 1.5 has gone to 1.3. You may remember the stability is 1/4 and then epsilon by 2, right? So so 0.22 is 0.25 minus epsilon by 2, right? So epsilon should be something closer to 0.06, right? So closer to 0.06, and then when we do that, then so that's closer. But now suppose I want to find it more accurately. Okay, I want to actually find it using a numerical criterion. To use a numerical criterion, I have to be slightly clever. Okay, so, and I will explain to you what that thing is, but over here I will just say GG, and over here I will say global GG, and this will allow me to set it from outside. Okay, and then let me go back to this figure here and explain what I am going to do. So if I am going to do a numerical calculation, you must remember that the eigenvalues are there is the unit circle for reference. So in the stable regime, the eigenvalues are like this. Okay, so they are plus minus some number. Let me say pi. Okay, so they're plus minus pi. And then once it becomes unstable, then it goes like this, and it becomes 1 plus, this is 1 plus minus pi, these eigenvalues, close to 1, very, very close to instability, it's like that. And then over here, it is 1 plus minus q, something like this. Okay, so the difference lambda 1 minus lambda 2 over here is something like 2 pi, and over here it is something like 2q. If I square this, then I get negative. If I square this, I get positive. Okay, because for Newton-Raphson, I need a differentiable function. If I plot, delta equals 0.22 fixed, this is epsilon. Okay, and over here, if I plot, let us say, max absolute value of lambda, then somewhere near 0.06 it will come like this, and then maybe do something like that. So it is not differentiable over here, and I will not be able to use Newton-Raphson method. However, if I plot lambda 1 minus lambda 2 square as a function of epsilon, in that case it will cross 0 because of this reason. When the eigenvalues are real, then the difference, the square of the difference is positive. When the eigenvalues are complex, then the square of the difference is negative. Okay, so now the square of the difference, eigenvalues are always complex conjugates, you see. So the square of the difference is going to be a perfect negative number. All right, I will come here to Newton-Raphson, and first I will, Newton, I hope Newton is here, it should be here, there it is. So I'll come here and I will write a new file, and this file will be called z equals fb x, and I will say global gg and gg equals x, and then I will say E. I need to define what OP is, so I will say OP equals that, and then copy that over here. Okay, so now I've got the monodromy matrix. Then I will say D equals eig E, and then I will say Z equals the real part of D1 minus D2 square. Okay, and so now if I try, for example, FB 0.04, then I get a negative number, and if I do FB 0.07, then I get a positive number. And then if I say Newton FB 0.06, then that's the answer. Okay, so let me save this answer now, and let me go back to Mathieu and remove this part and put the correct answer. So this is exactly on the stability boundary. Okay, so what does the solution look like on the stability boundary? To understand that, let us look at the monodromy matrix. So once again, that global part I have removed. I hope you are following. So now if I look at the eigenvalues of E, they are basically 1 and 1. They are fairly close to 1 and 1. It's not exactly correct. This is because of numerical errors, but because they split, you see, so it's more like 10 to the power minus 6 instead of 10 to the power minus 12. Why is that? It's because if you are trying to find the solution of this, then the solution is actually plus minus square root of epsilon. So if 10 to the power minus 12 is your error, then when eigenvalues are splitting, that is the sort of thing that happens. If you think about it, you'll see why it happens, but I can't go into further detail here. But since this is very, very close, what happens is I have two eigenvalues that are both close to 1. If I have two independent eigenvectors, it is okay, but you will see that I don't. So when I look at VD, you will see this is basically 1, 0, and this is minus 1, 0, which is the same as 1, 0. You see, so these eigenvectors, eigenvalues are nearly identical and eigenvectors are nearly parallel. Actually, there is only one eigenvector. It is more correct to think about this in terms of Jordan canonical form, which means that there should be polynomial growth, in this case linear growth. And so if I take this Tx and I start it with some random initial condition, what I should observe is linear growth. And we do. So you see there is linear growth. I can make it a bit longer. Okay, linear growth. So this is what we have done so far. We have done, move this a bit here. So we have done nature of solutions in unstable region, solutions grow linearly on the stability boundary. These are two things we have seen, and now the last thing I want to show you is the nature of solutions in the stable region, right? So stable region. So let us try delta equals 0.17, epsilon equals 0.05. Based on our previous calculations, we expect solutions here to be stable. Okay, so let us go back to MATLAB. Close that here. Delta equals 0.17, epsilon equals 0.15, and let us look at solutions. And well, maybe not that much, maybe 10 pi is good enough. And you see that they look almost periodic, but they're not really periodic, right? So if you look for 40 pi, so you can see it's not really periodic, right? It's got other frequencies in it, and we don't exactly know what those are yet, but we can think about them. And one way to do it is to think of a solution that starts not with some random initial condition, but the initial condition 1, 0. So let us start with the initial condition 1, 0. And here is the solution. So we are getting some solution like this. Remember, the initial slope is 0. Okay. How do we understand this solution? So one way to understand this solution, these solutions in the stable regime are actually called Mathieu functions. So these are classical functions. So if you like, then you can study these. There are books on them. Okay. but we will take a more of a practitioner's view, and what I will propose to you is that a solution can be found, can be sought of the form sum of a k, so k from 1 to n, no, k from I think we will try this. I think we will try 1 to n. Okay, so no, I'm making a mistake. It has to be minus n to n. Okay, because it is not periodic. So we can try a solution of this type: ak cosine beta plus k t. Let us try this solution, and beta to be found and ak to be found. What you will notice, this is again a harmonic balance type of approximation. You see, the reason is when beta is 0, if beta is 0, then cosine of kt and cosine of minus kt are the same. But if beta is equal to 1 over square root of 2, let us say, in that case plus k and minus k are different, and that is why we are keeping both negative and positive. This is really a truncated series, right? Actually, we want n going to infinity, but you will see that we don't need very large n. Okay, so let us now come here and go to maple, and let us say restart, and let us say delta equals 17 by 100, epsilon equals 0.05 is 1 by 20. Okay, then I say x double dot is equal to, no, sorry, that's not what I want. I want dE is equal to diff x of t dt plus delta plus epsilon times cosine of t times x of t. Now that is the thing that will be 0, and I say n equals 4, let us say, and then I say xs is equal to add ak times the cosine of beta plus k times t. What did I write here? Yes, k equals minus n to n. This is my approximate solution. I still don't know beta and I don't know the coefficients. There are 9 coefficients here. Okay, very good. What do I do next? I say dEA is equal to expand, substitute x of t equals xs in dE, and then I say combine trig. Okay, so I've got somewhat large expressions, but not to worry. Alright, very good. Let's see if I can pull out coefficients. So what I will do now, which are the coefficients I pull out? I pull out the coefficients of the harmonics that I have kept here. Yes, so those are the ones I pull out. And so how many do I have? Let us see how many we have. Okay, so 9. So I say with lin alg, then I say k equals matrix 2 times n plus 1, 2 times n plus 1. Okay, then I say for k from minus n to n do temp is equal to the coefficient in DEA of the cosine of beta times t plus k times t. Let's see if it pulls those out first, then we'll do something else. So it's pulling those out, there's no problem. Okay, so then we will say for m from minus n to n do, and then I will say capital K, and when this is minus n, so I have to go n plus 1 plus k. Okay, so that is the row, and the column also has to be n plus 1 plus m is equal to the coefficient in temp of am, and I can suppress this display, and then I can say eval k. Okay, so here's k, and you will notice that the delta and epsilon have been entered, beta has not been entered. When we were looking for the periodic solution on the stability boundary, we wanted a relation between delta and epsilon, but beta was known. It was known that the period is either 2 pi or 4 pi. Here it is not even a Fourier series. This is a quasi-periodic solution, right? Beta need not be an integer. It need not even be a rational number. In fact, when you think about the eigenvalues on the circle, you know that on one stability boundary they are here and another they are here, but typically they are here and here, right? So this is e to the power I theta for arbitrary theta between 0 and pi. Okay, so for this reason the solutions are in fact generally quasi-periodic. If they are rational, they are technically, if the theta is a rational fraction of pi, then it is technically periodic, but you know, they are rare cases. So mathematically the irrational cases are much more common, and these are all generally loosely called periodic solutions, quasi-periodic solutions, I'm sorry. Now over here, for this coefficient matrix, to have non-zero solutions for the A's, the determinant of this needs to be 0. So I will say DEQ equals the determinant of K. Okay, so there it is. And then I will say DIGITS equals 25, just to be safe. And then I will say eval F solve DEQ beta. Okay, so we will get several solutions, and the important one is 0.417. Okay, then you see 1.417, 2.417, they are all appearing. That is because over here, if I take beta plus 1, beta plus 2, and beta plus 0, and beta minus 1, and beta minus 2, I can shift beta by 1. If this is an infinite series, in that case all of those betas are solutions, you see. So that since the coefficients are expected to decay rapidly, for this reason it's almost a solution. So this 0.417 and this 1.417 and the 2.417 and the 3.417, they are essentially the same solution. This 4.417 has become 4.413, that is because of truncated series. Similarly, I have a 0.58, 1.58, 2.58, so they are really the same solution. So now the question is, what happens? What is the relation between this one and this one? And so let me call this one P equals and make it a list so that we will have an easier time pulling things out. Now, what is the relation between P1 and P2? And you may have noticed that P1 and P2 are equal to 1. And why is that? That is because That is because over here in the cosine, let's verify. I think P1 and P2 are 1. P1 plus P2 are 1. Okay, so you can see that. And so the reason that happens is because if I replace beta with 1 minus beta, that 1 gets absorbed into the integer, and the minus beta, because there is a cosine, we can just change the sign back. So that is why these answers keep coming. So they are, all of them are really effectively just signaling the same solution, and so the first one is the one that we are interested in. Very good. So now what we will do here is we will substitute. I don't know whether this will work. Let us see. Beta equals P1 in K. It may not work. Sometimes this works. No, that's not correct. That worked. Okay. So now I have substituted this. Now the eigenvector represents the solution. So if I say eigenvectors, I think I have to say eigenvects of the previous, there. Okay. So one eigenvalue should be close to 0, right? So now here is the eigenvalue, here is the multiplicity, there is the eigenvector. Okay. Now here is the eigenvalue, this is the multiplicity, and this is the eigenvector. Okay. And you can see that over here 989 is big and so many of the others are really small. So all I have to do is take these. What are they? A minus 4, A minus 3, A minus 2, A minus 1, A0, A1, A2, A3, A4. Okay. So here we are. Now let me come to MATLAB here, and I will say A equals, and I will, well, that didn't work, did it? Copy, paste. That didn't work. Okay. Paste. That didn't work. No wonder the other one didn't work. Okay. Here is the eigenvalue. This is what I am interested in. Control C. That's not working. I'm wasting time now. Let's copy the whole thing and see if we can get something with that. Well, let's try that first. First one. That worked. Well, let me do that. I don't think there's any difference. Here's the next one. I now realize there are probably better ways of doing this, but here's the next one. Here's the next one. Here's the next one. This is the eigenvector corresponding to the 0 eigenvalue. I hope that is clear to you. nearly there. 2 more. Although the last one, there's no real point in plotting it, but since we have come that far, we will plot it. Okay. All right. And we have to define beta equals, so that's beta, of course, is just that. We have more digits than MATLAB uses, but that's okay, it won't complain. Okay, so now I have a solution. I say x for k equals -4 to 4. I will say x approximate equals 0. I will say x approximate is equal to x approximate plus a k plus 5 times the cosine of beta times t plus k times t. End. Alright, so I have my approximate solution, but remember these are all cosines, and so the initial condition has to be seen at t is equal to 0, and this is just some negative number, so I will say xa is equal to xa by answer, so that I've normalized it, and now the initial condition is 1. And now when I plot tx and t and xa, I should get a very good match. This was all it was about. Well, there are two parts here. This is because I'm plotting x, only x. Now there are two curves there, right? So you can see that it is impossible to tell them apart on this scale, but when we zoom in a lot, and a great deal, then there is a difference. Okay, so there is a difference, but it's a very, very tiny difference. So that's the nature of solutions. The nature of solutions, the Mathieu functions are actually a series like this, but the beta is some fractional value. In this case, for these parameter values, as we have noticed, beta is like this. So it is not some, typically it's not a rational number. Okay. So now we have numerically studied the nature of solutions for the Mathieu equation. Let us return here. So there are unstable regions, and in those regions the solution has an exponentially decaying part and an exponentially growing part, and it's real, and depending on whether the eigenvalues are negative or positive, it is basically like an exponential function multiplying a periodic function of 2 pi or 4 pi or capital T and 2 capital T. And then you can, if you just start it from an arbitrary initial condition, then you will see it growing exponentially. Then there are the stable parts, and the stable parts here, I'll use this other color in the stable part. In the stable part, the solution looks like this, except this beta has to be found, and we can find it using the same harmonic balance calculations that we have seen. Additionally, if we do numerical calculation, then we want to find a point on the stability boundary like that, then we can set up a function like we had done earlier with the global one, and then we can integrate things. And there is a small trick we use with the eigenvalues, which have to do with the square of the difference of the two eigenvalues. That's a small trick for this problem, and then we can construct a function that crosses 0 at the place where we want it, and then we can use Newton-Raphson. Of course, there are other ways to do it, but this way is consistent with things we have already learned in this course. All right, that's it for today. Thank you.